I was sitting at my desk this morning just looking around the room, trying to do a little mental exercise. I wanted to see if I could spot a single object that wasn't in some way connected to one specific substance. And honestly, I completely failed.
It is much harder than people think. It's actually a pretty humbling exercise.
It is. It's in the plastic of my keyboard, it's in the finish on the desk, the synthetic fibers in the rug. And obviously, it's the energy that keeps the lights on and the delivery trucks moving outside. It is basically the invisible scaffold of the entire modern world.
That's a perfect way to put it. It's the ubiquitous backdrop to our lives. But the thing that stands out when you really dig into the research like we did for this deep dive is that for something so essential, most of us have a massive blind spot about where it actually comes from.
Right. We treat it like magic. We pump it at the station, or we buy the water bottle, and the backstory is just blank. But today, we are filling in that blank. We are doing a deep dive into the life cycle of petroleum. And looking at these sources, this isn't just about gas prices or geopolitics. This is a story about deep-time geology, extreme engineering, and frankly, some mind-bending logistics.
It's a journey that spans millions of years and usually ends at your local corner store. It is, quite literally, a geological time capsule that we're cracking open every single day.
And we have a massive stack of notes to get through, from the biology of ancient oceans to drilling rigs operating miles underground. But before we get to the heavy machinery, I want to start with something that I found right at the top of the research, the word itself, petroleum.
It's a great place to start. It's one of those words we hear constantly but rarely actually dissect.
Exactly. I've said it 1,000 times, but I never realized it's just a compound word hiding in plain sight. You break it down, petra and oleum.
Right. Classic Latin roots, petra meaning rock,
And oleum meaning oil.
rock oil.
It literally just means rock oil, which is such a brilliantly simple description for something so complex. It tells you exactly what it is, oil that comes from rocks, but it doesn't tell you how it got there.
And that is the first big misconception we need to clear up. Because if you ask the average person on the street what that rock oil is made of, what do they usually say?
They say dinosaurs.
Hmm?
I mean, I grew up with the cartoon idea that I'm putting a melted T-Rex into my gas tank.
It's the classic fossil fuel branding. It paints a great picture, but while it is technically fossils, the research makes it clear we aren't talking about a T-Rex, we aren't talking about brontosauruses.
So let's look at the actual recipe for this stuff. If we go back into the deep timeline, millions of years ago, what are the actual ingredients involved here?
We're looking at microscopic life. Ancient oceans were absolutely filled with tiny plants, algae, bacteria, and plankton. The sheer volume of this biomass was incredible.
Okay, so not a giant lizard, but trillions of tiny organisms floating in the sea.
Exactly. And here's the key mechanism. When these things died, they sank to the bottom of the ocean. Now, normally, in a forest or a standard ocean environment, things rot. They decompose. Nature recycles them.
Right, usually bacteria eat them and they disappear.
But in these specific ancient environments, the dead matter didn't just rot away. It settled into the seabed and was mixed with sand and mud. And crucially, it got buried before it could fully decompose.
Like it gets locked in.
Buried deep. And this is where the geology starts to act like a kitchen. Over vast stretches of time, that mixture of organic remains, sand, and mud gets covered by layer after layer of sediment. Then rock.
I was reading this part and picturing a massive geological lasagna. You just keep adding heavy layers on top, one after another.
That's a very accurate analogy. And think about the physics of that lasagna. What happens when you stack huge amounts of heavy rock on top of something?
You get pressure, massive crushing pressure.
And heat. The deeper you go into the earth, the hotter it gets. So you have this organic sludge trapped in what is essentially a pressure cooker. And that environment, over millions of years, changes the chemistry.
It cooks it.
Essentially, yes. It transforms that biological matter proteins, carbohydrates, lipids, into hydrocarbons. It turns into a thick, dark liquid containing sulfur, oxygen, and other elements.
And that liquid is the petroleum.
That is the rock oil. It's fundamentally just ancient sunlight and ancient life, squeezed and cooked by the weight of the earth until it becomes liquid energy.
It's wild to think about that compression. You're taking millions of years of biological history and concentrating it into this dark sludge.
It definitely changes your perspective on your morning commute. You aren't just burning fuel, you're burning history. You are releasing energy that was captured by algae millions of years ago.
But here's the thing. If this process requires ancient oceans and specific burial conditions, that means it's not just everywhere, right? I can't go into my backyard, dig a hole, and strike it rich.
Unfortunately not. The geographic distribution is very specific because the geological history of the planet is specific. The notes highlight that the major reserves we tap today, the Middle East, North Africa, North America, Russia, these are places that at one point in deep time had those perfect conditions.
So those are the hot spots. But knowing generally that the Middle East has oil is one thing. Finding the specific spot to drill is a completely different problem. Because we're talking about reservoirs that are miles underground, right?
Correct, and they aren't marked with an X on the surface.
This feels like finding a needle in a haystack, except the haystack is made of solid granite and the needle is liquid. How do we actually find it?
This is where the science of exploration comes in. It is a massive detective job. We rely on geologists.
The rock detectives.
In a way, yes. They don't just guess.
Yeah.
They study the surface rocks to recognize specific types that are likely to contain oil. They look for the clues in the geology that suggest that ancient pressure cooker environment existed right there.
The sources mention surveys. What does that look like practically? They aren't just walking around with magnifying glasses.
No, it's high-tech. They map the subsurface structures. They are looking for specific trap shapes in the rock layers where oil might have pooled and gotten stuck, prevented from rising to the surface by a cap of impermeable rock.
But even with the maps, you don't know for sure until you actually go there.
Yes, right. That's the catch. You can have the best data in the world, but until you physically drill into the rock, it's all theoretical. That's why the industry calls it an exploratory well.
A test drill.
It's a high-stakes verification. You drill the well. If you hit the reservoir and the oil flows, what they call a strike, then you can move to production. If not, it's a dry hole and you've spent a lot of money for nothing.
Let's talk about that drill, because this is the part of the research that really surprised me. I think when people hear drilling for oil, the mental image is still a bit primitive. Maybe like a water well, a bucket on a rope, or a simple hand-cranked auger.
Yeah, the reality is a long way from a bucket on a rope. We're talking about some of the most complex mechanical engineering on the planet.
It starts with the tower, right? The drilling rig.
The rig is the visible part on the surface. It's the factory floor, essentially. But the real work, the actual boring, is happening on their site.
The text describes the process as boring. Not boring as in dull, but boring as in tunneling. Walk us through the mechanics here. How do you chew through solid rock?
It all comes down to the bit. At the very bottom of the hole, you have the drilling bit. It's a specific tool designed to crush, grind, or cut through rock layers.
The tip of the spear.
Right. And that bit is attached to a hollow steel pipe. Up on the surface, on that rig tower, there is a massive motor. That motor grabs the pipe and spins it with incredible torque.
So the motor spins the pipe spins the bit, and the bit grinds the rock into dust.
Simple in principle. But here is the complication that the notes emphasize. Depth. As you drill deeper, you can't just use one long, continuous piece of pipe. You'd never be able to transport a single pipe that is 3 miles long.
So they have to build the pipe as they go.
Exactly. It's a modular process. They drill down the length of one pipe section, usually about 30 feet or so. Then they stop the motor, unscrew the top drive, grab a new section of pipe, screw it onto the top of the string, and start drilling again.
It's like a giant vertical erector set. You're just threading pipe onto pipe, pushing the bit deeper and deeper.
And the scale of this is hard to wrap your head around. The sources mention that the deepest wells can be over 5 kilometers deep.
5 kilometers. I tried to visualize this earlier. Think about a 5K run. That's a decent workout. Now, imagine that distance, but straight down into the crust of the earth.
It's staggering. And think about the mechanics of that pipe. If you have a steel pipe that is 5 kilometers long and only a few inches wide, it's not a rigid stick anymore.
Right. At that length, the physics must get weird. Is it flexible?
It behaves more like a spaghetti noodle than a steel rod. The engineering required to rotate that string from the surface, transmit that torque 5 kilometers down without snapping the pipe, and keep the bit grinding on target. It's a marvel.
It really is. You're remotely piloting a robot through rock, miles away from where you're standing.
Precisely. And you are doing it blindly, relying on sensors and physics to know what's happening down there.
Okay, so we've bored through the rock layers. We've gone down the 5K run. We finally hit the target, the reservoir. What happens in that moment? Is it just a big underground cavern filled with black liquid?
That's another common misconception, the underground lake idea. It's almost never a big open cavern.
So what does a reservoir look like?
Think of a hard sponge. It's solid rock, but it has tiny pores, microscopic holes. The oil is trapped inside those tiny pores, soaking the rock.
Got it. So we drill into this oil-soaked rock sponge. Now, earlier we talked about the pressure cooker. Does that pressure come back into play here?
It's the most important factor in the extraction phase. That pressure didn't go away just because we drilled a hole. The oil has been trapped there under the weight of miles of rock for millions of years. It is desperate to escape.
So when the drill bit breaks through the cap rock and enters the reservoir,
It's like pricking a balloon, or use the classic analogy from the research, shaking up a soda bottle and then cracking the lid. The pressure inside the reservoir is much higher than the pressure in the borehole you just drilled. So physics takes over.
the pressure pushes the oil out of the rock and up the pipe towards the surface,
Exactly. That is striking oil. In the early days of the industry, you didn't even need pumps. The earth just threw the oil at you because of that pressure differential.
which brings us to that Hollywood image, the gusher. The oil shoots into the sky, it's raining black gold, and everyone is dancing and celebrating.
It's a very dramatic image. But in modern engineering terms, a gusher is a disaster. It's a total failure of control.
Because you're dealing with explosive materials at high pressure.
Right. If that oil rushes up uncontrolled, it can destroy the rig, cause massive fires, kill people, and ruin the environment. The modern game is all about containment. You never want to see the oil spraying into the air.
So how do they stop the soda bottle from exploding?
Valves. They place a complex system of valves right over the top of the borehole.
It's like a sophisticated cap.
Exactly. The text uses a really relatable analogy here. Once those valves are in place, the flow of oil can be controlled like the flow of water from a kitchen tap.
That is such a wild contrast. You are harnessing this geological force, millions of years of pent-up pressure, and you're regulating it with the same ease as turning on a faucet.
It's the ultimate taming of nature's forces. You're converting geological chaos into a steady, manageable industrial flow.
So we've got the flow, we've tamed the pressure, now we have this black liquid coming out of the ground. This is the moment where I ask, can I put this in my car?
Definitely not. Do not put this in your car. It would destroy the engine immediately.
Why not? It's oil, isn't it?
It's crude oil. And the name is accurate. It's crude. It's a dirty mixture. It's full of impurities, sulfur, and different types of hydrocarbons all jumbled together. It's just the raw ingredients.
So extraction is really just the first chapter of the book.
It's just the beginning. Now we enter the logistics phase. And this is a global relay race to get that crude to a place where it can actually be made useful.
Let's trace this path. We're at the rig, maybe in the middle of a desert or out at sea. Where does the oil go first?
Step one is usually pipelines. The oil is pumped from the wellhead into a network of pipes,
The pipeline highway.
which usually leads to a destination called a terminal. These are those massive tank farms you sometimes see, usually located on the coast.
Why the coast? Is that just for convenience?
It's strategic. The global oil market relies on the ocean. To move oil efficiently around the world, you need ships, giant tankers.
Ah, right. So the pipeline feeds the terminal feeds the tanker.
And these tankers are behemoths. They are some of the largest moving objects made by humans. They carry this crude oil across oceans to its final destination, the refinery.
And this brings up an interesting point about the geography of oil. The place where you dig it up isn't usually the place where you use it.
Rarely. You might extract crude in the desert of the Middle East, pipe it to a port, ship it across the Indian Ocean and through the Suez Canal just to refine it in a facility in Rotterdam or Houston.
And the refinery is where the magic happens. This is the factory.
It's a chemical engineering complex. This is where they take that duty mix of crude oil and separate it. They heat it up and split it into its useful components: petrol, diesel, jet fuel, chemicals for plastics.
It's amazing to think about the mileage on a gallon of gas before it even gets to your car.
It really is. It's traveled thousands of miles, changed forms, moved from rock to pipe to ship to factory, just so you can drive to the grocery store.
And speaking of buying it, there's one last detail in the notes that caught my eye. It's about the way we count this stuff. When we hear about oil prices on the news, they don't talk about gallons or tons.
No, the standard currency of the oil world is the barrel.
Oil is trading at X dollars per barrel. It feels so old school. Do they actually use physical barrels anymore?
Not really. You don't see wooden barrels rolling around on the decks of ships. It's mostly pumped into massive tanks now. But the unit of measure stuck from the early days of the industry in the 1800s.
So it's a ghost unit, a reminder of the history embedded in the industry.
Absolutely. It's 42 U.S. gallons. That's the magic number that rules the global economy.
So let's zoom out for a second and look at this whole picture. We've gone from ancient plankton dying in a prehistoric ocean to being buried in a geological lasagna to being cooked by the Earth into a high-pressure liquid.
To being hunted by detectives using sound waves, drilled by 5-kilometer-long robot strings.
Hyped to the coast, shipped across the world in floating cities, and refined into the plastic on my desk or the fuel in my tank.
It is a staggering sequence of events, and what stands out to me is the coordination. It requires biology, geology, physics, heavy engineering, and global logistics all working in perfect sync.
It makes you look at that plastic pen or that tank of gas a little differently. We usually think of oil as just a commodity, something cheap and dirty. But when you look at the life cycle, it's an engineering marvel.
And a geological wonder. We are essentially running our modern world on the compressed time capsule energy of the ancient world.
So here's my challenge to you, listening right now. The next time you fill up your car, or look at a plastic bottle, or even just turn on the heating, spare a thought for the journey.
Think about the 5 kilometers of rock. Think
No.
about the pressure.
Think about the kitchen tap holding back the force of the earth, and ask yourself, if it took millions of years to make and a global fleet to deliver, what else in your room has a secret history that deep?
It's a question worth asking.
That's a wrap for this deep dive into the life cycle of petroleum. Thanks for exploring the depths with us.
Always a pleasure. Keep questioning what's beneath the surface.
See you next time.